Again, welcome back to SBR physics classes. Today, we will give finishing touch to the radiation. Let's start the first concept. Okay. In the last class, so we have learnt. So on any object, suppose radiations are falling, some part of the radiation will get reflected, some part of energy in the form of radiation get reflected, and some part of energy is absorbed here only, some part absorbed here, and some part is transmitted. These three phenomena will happen. Like this is a transmitted energy, it is a reflected energy, some is being absorbed also, and total amount of energy incident, let this be Qi. Right? So depending on nature of the material, this R, A and T will distribute the total energy Qi. Total Qi is there, and depending on nature of material, what is R, what is A, what is T, that will be distributed. Okay. Now I told you earlier, what is R? It is the reflective power. What is R here? It is a reflective power. Reflective power is, you have already learned. What is that reflective power? It is represented with small r. Total amount of energy reflected in the form of radiation with respect to total energy absorbed. And what is the absorptive power? Absorptive power is, we say A, it is total energy absorbed by the body with respect to amount of total energy incident on it. Then one more is transmittive power. It is we represent with the T here. The amount of energy transmitted with respect to total amount of energy incident. These things, again, just I have refreshed. Okay. Now here, if I add this value of R plus A plus T will be equals to 1. If you remember one thing, the energy associated with reflectance, the energy going this side is this much, the energy is being absorbed will be this much, the energy transmitted will be this much. Definitely this energy will sum up to total incident energy, right or not? The energy, these will be equals to total incident energy. Now here you can, R is what this, if you add all those, then Y you will get 1, you will come to 1. If you want, you can add 1 in place of R, what you can write? QR by Qi plus QA by Qi plus this is QT by Qi. Then you can get to know here Qi, if I 1 by Qi, if I take common, then what is in bracket? QR plus QA plus QT, that is equals to what? Qi. Then what is the answer here? 1. Therefore, the reflective power, absorptive power, transmittive power is equals to 1. That we say. Okay. Now, let me move on. One definition I would like to go for here. What is emissive power? Let us go now. Emissive power. Okay. So any object at the temperature T always radiates energy. It always radiates. You know, any object at a temperature more than 0 Kelvin, it will always radiates energy. Here important, the amount of energy emitted in the form of radiation. That amount of energy radiated depends on surface area. More the surface area, it will emit more, and even it depends on temperature also. More the temperature, so at any one time, if you take, more energy will go away in the form of radiation. So even time, more the time, then even it depends on the time also. Even it depends on the nature. Sorry, it depends on the surface. It depends on the nature of surface. Some surfaces are polished, some surfaces are rough, some surface depending on the nature of surface, the energy radiated also changes. That's the reason emissive power. How do you define? We define it in this way. It is the energy. Let me say emissive power is E is equals to, what is emissive power? Energy radiated out. Let this be Q. Energy radiated out per unit area per unit time. This is what we can call emissive power. Emissive power. So this emissive power, how much energy gone away in the form of radiation. So this is emissive power. How do you define? It is the energy emitted per unit area per second at any given temperature. If temperature is more, the emissive power will also becomes more, energy will go away, right? So ultimately, so what you can define here, for emissive power of a body is defined as, for a given temperature, right? Amount of energy radiated per unit area, radiated per unit area per unit area per unit time. This is we say. It depends on what factor? This emissive power depends on, firstly, this temperature. On temperature, more the temperature, more the emissive power. So again, secondly, it depends on nature of the surface. That surface is of which material, and whether that surface is coated, whether that surface is rough, whether that surface is soft. The nature of surface is also important. Nature of surface. And thirdly, how much area is exposed to the surrounding. More the area, then the amount of energy radiated away is also more. So exposed surface area to the surrounding. Exposed surface area, right? Okay, if you take a cup of tea, if the same tea, if you put it in a wider bowl or in a tray, then that tea will suddenly, it will radiate more and then it will cool very soon. More the surface area, then radiation going away is also more, the energy lost is also more quickly. So ultimately, the emissive power is defined as amount of energy radiated per unit area per unit time at a given time. If more the temperature, more the emissive power. So it depends on temperature, it depends on nature of surface, it depends on exposed area, right? Okay. Now this is what would be unit of this emissive power? The unit of this you can write what? Definitely here joule. The unit will be what? Unit of this will be unit is what? Joule per meter square per second. So it can also be, you can write it even like that also. It is joule per second is watt per meter square. This is the unit of emissive power. Right? Okay. Now we will go to the black body. Okay. Black body. Okay. So what is black body? any object, any material which absorbs all the radiations which incident on them, then we say it is perfectly black body, right? But practically in our universe, we don't find a ideal black body, because any object you take, at least some percent of the incident radiation it will reflect. It will not absorb all. You know, no object. You can take any object. They are not perfectly, ideally black body. Okay, you can have practically some lamp black or platinum powder, platinum black powder. They are practically 96, 97% of total incident energy they can absorb. They are, we can say, for absorptive perspective, they are very close to the black body. And that too, in our practical, these two examples we can give, what is lamp black and then platinum black. They can absorb 96 or 97% of total radiation incident on them. But even there also problem lies here. They can absorb 96% of total energy incident on them, but once you heat them, they are unable to radiate all the radiations, all possible radiation. They can absorb 96%. When you heat them, they are unable to radiate. When do you say perfectly black body? Once the radiations falls on it, it has to absorb all the radiations. When you heat it, in turn, it has to emit all the radiations. For emission also it should be ready, and for absorption also it should be ready. When all the radiations fall on it, it has to absorb, and when you just heat it, then it has to give away all possible radiations it has absorbed, all possible radiations it can emit. For emission is also and absorption also, in both the way, if it is okay, then we can say it is a perfectly black body. So in practical universe, we don't find ideal perfect black body. Even you take black hole can even pull even waves also, light also. It can pull even radiation also, but it can absorb everything which comes towards it, but it is unable to emit anything. When do you say perfectly black body? When it is allowed to absorb, it has to absorb. When you make any radiations to fall on it, it has to absorb. When it is emitting at any higher temperature, it has to emit all possible wavelengths. It has to emit all possible wavelengths, and even if any radiations fall, it has to absorb all. So emission and then absorption, both way it should be okay. Then we say it is perfectly black body. But black hole is only absorbing. For absorption, I can say it is a black body absorb, but for perfectly black body, it has to be ready for both. It will not emitting anything. So here, one Ferry, the name of scientist Ferry, he has designed one device that will act like a perfectly black body for 99.9% of absorption. Let me go for Ferry's black body, and he has designed one device that will act like a almost ideal perfect black body. We will see now. What is black body? The body which absorbs all the radiations which incident on it. This is black body. Practically we find lamp black and platinum black are near perfect black body for absorption. They absorb 95% to nearly 97% of radiations which incident on them. Right? Okay. Now, we have already learned absorptive power. For perfectly black body, absorptive power is unity. You already learned what is the absorptive power of a material. It is total amount absorbed divided by total amount of energy incident. This is the absorptive power. You have learned now itself. Then what is the absorptive power of the perfect black body? Here, how much has been incident, that much will absorb. So here absorption will be equals to Qi. So Qi by Qi will be what? 1. That's the reason I'll write absorptive power of perfect black body is unity, right? I told you. Okay. Now I'll go to the Ferri's black body. Okay. Here I'll write here only Ferri's black body. The scientist named Ferri, he has designed one device in lab, and it will act like a almost perfect black body. So to whom we call perfect black body, which absorb all the radiations falls on it. When it is allowed to emit, it should emit all the radiations both way. Okay, how he has designed here. Here this is the device what he has made. Here one projection, conical projection he has taken. Okay, this is okay. Okay, here he has painted lamp black. He has painted with lamp black here in the interior. Here one conical projection is made here. So what is the intention of that is, suppose any ray which incident. So this is the hole. Any ray which comes inside, right? Any ray which comes inside, okay, you know lamp black can absorb 95% of total radiation incident. So here it will reflect. Why this projection is made? The ray should not reflect back again and to go through the hole. The projection is made so that light can reflect, and then here only it should move. It should not go back directly to the hole and outside. It reflects here, and further it will reflect like that, multiple reflection. Remember, in one collision, how much the lamp black can absorb? 95%. Only 5% is remaining, and that 5% of energy it will collide with another place. Again, 95% of that 5% is absorbed there itself. Like gradually in multiple reflection, all energy is being absorbed. So here important here. So here here is cavity. Here is vacuum is created. By vacuum is maintained. Evacuated is vacuum here. Why it is vacuum here? Because to avoid the energy loss due to conduction and convection. Here vacuum is maintained. Here important, this is, we can say, incident radiation. What you say it is? Incident radiation. Okay. Now here, which is perfect black body here? Not this whole device. This whole acts as a perfect black body. Why this hole acts like a perfect black body? Because this hole is considered like a black body. Any ray which incident on that hole, it is being gone inside, and in multiple reflection, the all energy is trapped inside. With here, if you see the hole, whatever energy comes, it will go inside. Okay, all is being absorbed. When you heat this device, and take it to the dark room, then in the dark room you will find this portion only bright. When you heat it, Anyhow, it has absorbed enough. When you make all radiations continuously to go inside the hole, when you make this lamp tank to absorb, okay, anyhow, it has absorbed enough. Then when you take this device and heat it, and when you take it to dark room, then the one which absorbs it can emit also. The perfectly black body is the one which can absorb all. When it is allowed to absorb, when it is heating, it will emit all. So when you heat it, this in the dark room only whole will looks bright, rest part will be dark. Then whole is here, not all full here. This is Ferris device. The whole is only acts as a perfect black body. Here we can write whole acts as a perfect black body, not whole device, not whole device. This is it. This is a simple thing. Okay, he has done it. Other way you cannot find any body which is perfectly black body, right? Okay, sun is considered to be a perfectly black body. Sun, because it is at very high temperature, it is emitting all possible wavelengths. It is emitting all possible wavelengths radiation, and even you cannot avoid that whichever ray comes towards it, even can absorb also. Like even there might be some reflection and all. You cannot say it is ideally perfect black body. Sun is, but very practically all stars, sun. You can tell they are almost perfect black body, right? Almost. So we can give an example for perfect black body as sun. It is almost act like a perfect black body. It can emit all possible wavelengths. Okay. Now we'll move to the next thing here, Kirchoff's law. Okay, these plenty of theory will come here. Okay, you have to be ready for this more theory. Okay, now let me go to the Kirchoff's law. Okay, now to explain this, let me take one example here. Okay, I have got two bodies. One we have perfect black body. One is this is one perfect black body. Say its temperature is T. The another we have one any other normal body. Okay, say its temperature is also T. Both are kept in a surrounding. Right? Okay. Now the temperature of surrounding, let us say temperature of surrounding will be this. Okay. Now here one assumptions I would like to go with, that the dimensions of both are same. So size of both are same. Let me take here dimensions of both same. This is I am taking one example. Okay, dimensions both sizes are same. Okay, as the surface area exposed are same. Okay, one thing, if I am standing in this room, remember my body is receiving radiations from the radiations emitted by every part of this surrounding. According to Prevott's theory, you know it, every body at a temperature more than 0 Kelvin can emit the radiations. Even my body is also emitting radiations. At the same time, my body is receiving, absorbing radiations which are emitted by surrounding. That absorbing and emitting, it's a continuous process, it takes place continuously. Right? Okay. So even my body is emitting also, even my body is absorbing also. Okay. My body, my emission, radiation emission by my body doesn't bother who is there around. It only bothers about my temperature. The radiation emitted by my body depends on my temperature. So how much radiation, depending on my temperature, I have to radiate, I'll radiate. Whether I am standing in front of fires, whether I am standing in front of fire, I am standing in front of oven, I am standing in... No, radiation emitted, it's a property of mind. With respect to my temperature, how much I can emit, I'll keep emitting. My radiation emitted out my body, does not depend on who is around me. Okay or not? I keep doing my own, I keep radiating my body, keep radiating out. If outside body is at higher temperature, it will also give radiation. I'll absorb. Absorption is there, but radiation out of my body, no, I'll keep doing what I can do at my temperature. Radiation given out by body does not depend on whatever amount of radiation goes out per second of any body. It does not depend on who is around that body, or which temperature body is around that body. No, it's not matter. Okay or not? It can absorb. If outside radiations are coming on, falling on me, I can absorb, but I can radiate depending on my temperature. No one can stop my radiation going out. It depends on temperature. Depending on my temperature, how much I can radiate, I'll radiate it. That is there. This is Prior's theory. Now come to here. Perfectly black body. Here, surrounding. And if you keep these to for longer time, like in this room, every objects in this room are for long time they are there here, then temperature of the room is equals to temperature of the objects which are present in this room. Okay, this marker is, since long it is present in this room, so temperature of this marker is equal to temperature of the room. That is there. Likewise, after a long time, what will happen? Temperature of the bodies will be equal to temperature of surrounding. Both bodies will come in thermal equilibrium with surrounding. That is there. Okay. Now, due to this surrounding, the radiations which incident on both surrounding material also, whichever may be surrounding, they emit the radiation, they fall on these two bodies. Okay. The amount of energy incident on both will be same because surface area of both are same. So ultimately amount of energy incident on both is same because they are at the same surrounding temperature. Whatever energy falls on this, the same will be falling on this, because the dimensions of both are same, the area exposed is same, the amount of radiation they receive is same, area is same. So what I will write, the first point is, here again the radiant energy, what you say, radiant energy incident per second on black body will be what? Let us say Q1. On both, how much energy is incidenting? As far as energy incident is concerned, same, because the area is same and they are kept at the same surrounding temperature. So whatever energy falls on it, the same energy will fall on it. Radiant energy incident per second on black body is Q1. And in the same way, radiant energy, let me write commonly, energy incident on normal body per second is also same energy is incident on both. Now let me write another point here. Energy absorbed by black body will be Qi itself, because it is a perfectly black body. How much energy incident on it, it will absorb all. But what about energy absorbed by this normal body? Can you remember this formula? Amount of energy, this is absorptive power of this body. Absorptive power of a body depends on nature of material. Some will absorb more, some will absorb less. That is there. Depending on nature of body, absorptive power value will be different. So absorptive power of this A, absorptive power of this normal body is equals to amount of energy absorbed divided by amount of energy incident. This you already learned. Therefore, amount of energy absorbed is equals to, this is absorptive power into total amount of energy incident. So what is the amount of energy absorbed by this normal body? Energy incident, okay. Energy absorbed by perfectly black body is what? Energy absorbed by black body, perfect black body per second. Can I write energy absorption is Q1, black body it is. In the same way, energy absorbed by normal body per second will be equal to what? Absorptive power of that body into total amount of energy incident. This is there. Okay. Now come to one point here. As temperature of the bodies are not changing, right or not? When temperature of bodies are not changing, how much it is absorbing, then it has to emit the same in any 1 second. Then only temperature of body remains same. If it is absorbing more than emitting, then its temperature will increase. If its absorbing is less than emitting, temperature will decrease. So ultimately, if my temperature of this marker is same in this, means what you can understand, amount of energy absorbed by it in 1 second will be equal to amount of energy emitted by it in 1 second. Then only the temperature of this will be same over the longer time. Then with that point I tell you, energy absorbed by normal body, this is there. So what will be, since I'll write one point here, since both bodies are in thermal equilibrium, with surrounding, therefore temperature of the body is equal to temperature of the surrounding. If temperature of the bodies has to be same, means the energy emitted by both will be equal to their absorption. So what then, if temperature of black body has to be same, means energy emitted per second will be what? Energy emitted per second by black body will be equal to Qi itself. How much it has absorbed Qi? It has to emit in 1 second how much? Qi itself. Right? In the same way, how much it has to emit to maintain the same temperature? So for this normal body, right? For the normal body, energy emitted or radiated, energy radiated per second by normal body will be what? A into Qi. How much it has absorbed? This much in 1 second. The same amount of energy it has to emit out. Then only the temperature of that body remains same. Right or not? Okay, energy emitted per second is this. Now, you can remember emissive power definition now. What is emissive power definition? Rate of energy emitted per unit area per second at a given temperature. You already learned it. Now, emissive power of perfect black body. How do you write? I can write emissive power of perfect black body. You know what is the definition of emissive power? Amount of energy incident is the amount of energy radiated out. Formula of emissive power: amount of energy radiated out per unit area per second. If I take, let me write it like that. Okay. Okay. Now, in the same way, emissive power of normal body, emissive power of normal body. How much energy it is radiating out? A into, you already read, energy emitted per second by this normal body. Where is here? Let me here energy radiated per second by normal body is A into Q1. A into Q. Energy radiated out, area of both dimensions are same. Here 1 second I am working with. Okay. Now here energy emissive power of perfectly black body I will write with E into E subscript B, and emissive power of this normal body I will write E subscript. Okay, only E I will write for any body. Okay. Now if I divide both, you will get the equation for Kirchoff's law. When you divide this both, okay, let me divide this by this. E by EB, emissive power of black body, is equals to, if I divide this by this means QI cancels. This by this I am doing, what is remaining here? E. Okay, this further I can write it as emissive power of a normal body. You take here absorptive power. A is what here? Absorptive power of a normal black body is equals to emissive power of black body. This is what these things I done because to get this. Directly if I write it, you may not understand how it comes. This is an example will make us to get this form. Okay, what is this is very important here. This is Kirchoff's law. Okay, what is this emissive power of a body? This is absorptive power of a body. Okay, this is emissive power of perfectly black body. Okay, now these are all being done at one temperature. Okay, now with this equation we can understand this emissive power of a black body at a one temperature will be constant. Okay or not? Emissive power of a black body at one particular temperature will be single valued. But emissive power of different bodies at the same temperature are different. Perfect black body is single entity. Is emissive power of a perfect black body at a one temperature will be constant. But emissive power of different bodies are different at the same temperature. If I am talking about the 300 Kelvin, at the 300 Kelvin emissive power of different bodies are different. Okay, but this is constant. Emissive power of black body at a given temperature is constant. Now importantly, here emissive power of a body to the absorptive power of the body is always a constant. It means for any body absorptive power is more, emittive power is also more, emissive power. What is meaning of this one? Let me here, what is the meaning of this? Let me take here an example here. Okay, China dish. Okay, China dish, some like that, some China dish, some apparatus, some home purpose designing materials and all. Yeah, this is one China dish. Okay, here on this you will find some black paintings that do on China dish, or a one cup. You can say China dish, one China made cup. They make black paintings on it. Okay, that China dish, if you keep at room temperature, right? So that China, the black paintings made on that China dish will absorb more when you keep at room temperature. Who is absorbing? The black paintings absorbs more, or rest part is more? Black paintings absorbs more. When that China dish, if I on any apparatus of made China, if I keep the black paintings are made, if I keep it at room temperature, the black paintings made on it absorbs more than rest part of that China dish at room temperature, at the lower temperature, at any given temperature. Who is absorbing more? Black paintings absorbing more than rest part. Okay. Now the same China dish, if you heat it and take it to dark room, then definitely in the dark room you will find the black paintings looks very bright and the rest part you cannot see. Rest part is almost dim. Who is more bright? Black paintings are bright. So in the room temperature, who absorbed more? Black paintings absorb more, no? Compared to the rest part of the China dish. So who is absorbing more? Black painting is absorbing more in room temperature. When you heat it, when you take it to higher temperature and take it to dark room, which part of the China dish appear more bright? The color, the black painting which has been made, which appears more bright because it has absorbed more. In room temperature, who has absorbed more? The black painting has absorbed more. If you heat it and take to the room or take to the dark room, then who will become looks very bright? The dark painting looks very bright because it has absorbed more, it has emitting more. That's all. Whichever absorbs more, they emit more when it take it to the higher temperature. This is a Kirchoff's law. The ratio, this is anyhow, it is a constant, right? So whichever I got high absorptive power, it can even have high emissive power, right? Okay. Now one thing you have to be clear here. Remember here, absorptive power comes on behalf of external light. If you are not putting external light on any object, it will not absorb. Absorptive power and emissive power are totally different. Absorptive power is what? Absorptive power is equals to amount of energy absorbed to the amount of energy incident. If you are not making any incident energy, no question of absorption. Absorptive power comes on behalf of incident energy, but emissive power comes on behalf of its own temperature. Emissive power comes on behalf of its own temperature. If you take this marker in a dark room, it cannot absorb because in the dark room it is not receiving any energy. This marker, if I take in dark room, it is not absorbing anything because I am not making any energy emitting. Its emittive power depends on its own temperature, but its absorptive power depends on external energy which is incident on it. Both are different quantities here. Emissive power and absorptive power are different quantity, but combining and making here one equation. Here EB is absorptive emittive power of the black body, here emittive power of any given body, and it is absorptive power of any given body. So this equation tells you, so whoever good absorber, they are good emitter, right? You take sand. In the summer, sand will absorb more. Okay, your rate of absorption is more, then rate of emission is also more. In the night, it cools very quickly, right or not? If absorption is less, emission is also less. If it absorbs less, it will emit less. Right or not? Very clear. Okay. Here, this is there. Now, what you can conclude here, good absorbers are good emitter, we can say. Good absorbers are good emitter of radiations. Good emitters of radiations, right? Okay, this is it. One more, if you want, you can take one more example. Remember, you can even let me take one metal. Okay, here, so this is one metal. Everywhere polished, and only at one place only we have made black with platinum black. Here we have made black with platinum black. Here, this is one metal. This is one metal. Okay, this is one metal bowl. So at one place we have, with the help of platinum powder, we have made it black here, and we, at the room temperature we have kept it. Okay, at the room temperature we have kept it. Who is absorbing more here? This black, platinum black, it absorbs more than here is polished. We have polished it. Here is a platinum block. Who is absorbing? If I keep it at room temperature, who is absorbing more? The black, this platinum black. This platinum black absorbs more. Then after keeping in room temperature for sufficient time, now this block I'll take it to room, dark room. So who has absorbed more? This black has absorbed more. In the dark room, if you take, so who will emit more? This black will emit more, black, platinum black will emit more. Here in the dark room, this only appears brighter. This is polished. It is not absorbing anything, it is polished, very weak absorber. Here in this other part, no absorption, almost negligible absorption. So here platinum block absorbs more. So as it is absorbing more, when you heat it and take to the room temperature, from which side more energy will come out? So we have absorbed, you will emit more. So good absorbers are good emitter, right? So the same equation, this is for total emissive power and total absorptive power. For single wavelength also we can write it. For single wavelength, some material absorbs some wavelength more, and when you heat, they emit that wavelength more. For example, if you take one glass, suppose it is green color, you see, one glass, it is green color. At room temperature, if I see it looks green. Why it looks green? It has absorbed everything and it is only reflecting green. When I look at this, I'll feel it is green. Because green light only it is not absorbed, and after reflecting that green is coming towards my eye and my eye is perceiving it is green. Okay. Now, if I keep it this for a long time, okay, and it will receive, it will absorb, and green it will not absorb. Okay. Once I heat it, some temperature, I'll raise its temperature, I'll heat it, and I'll take it to dark room. The moment when I take it to dark room, it appears red. It appears red. Then what do you understand? So when it is in room temperature, it has absorbed red. Okay, when it has reflected what? Green. It has reflected green. Okay, then it has absorbed some other colors. When I heat it and take to the dark room, it is appearing red. Means what you understand from this? It has absorbed red when it was in room temperature. When you heat it, what it has absorbed, it is emitting. It has absorbed red, it is emitting in the dark room. After heating to it and then take to the dark room, it will give away red radiation. Then you can see it has absorbed red, it is emitting red. So even you can write it for wavelength also. In terms of wavelength, this Kirchoff's law you can write emissive power for particular wavelength and absorptive power for particular wavelength is equals to emissive power of black body for the same wavelength. Right? So which is absorbing more, it will emit more. That is equals to emissive power of black body, same wavelength, how much it has emitted, same wavelength energy, how much it has gone away from black body. This is all being done at one temperature T. Right? Okay, how do we state the Kirchoff's law? It is defined as it is defined for a given temperature for a certain wavelength, the ratio of emissive power to the absorptive power is equals to emissive power of perfectly black body at the same temperature for the same wavelength. This is Kirchoff's law. Right? What is Kirchoff's law? Is the ratio of emissive power of a given body for a certain wavelength and at a given temperature to the absorptive power for the same wavelength at the same temperature is equals to emissive power of black body for the same wavelength and at the same temperature. This is Kirchoff's law. Right? Okay. Now I'll move on. Okay, now I'll go to the one more definition. Emissivity. Okay, one more definition is emissivity. Emissivity of the body. We represent with small e. It is this emissivity just is a comparison between perfect black body and given body. Emissivity is defined as emissive power of a given body, emissive power of a body. You have to mention temperature at temperature T to the comparison emissive power of perfect black body at the same temperature. Right? You can write this as emissive power of a given body to the emissive power of perfectly black body. This is emissivity. It depends on nature of material. This emissive power is anyhow at a given temperature, this will be constant. This emissive power is more, then emissivity is also more. It's a comparative term, relative term, you can say emissivity is. Okay. Now, in Kirchoff's law, you have already learned already. In Kirchoff's law, you have learned one formula. Kirchoff's law, what you have learned there? Emissive power of given body, emissive power of perfectly black body is absorptive power. Now itself I have done it. Right on. Just A was here, BB was there. The same thing I written here. Now you can compare it. Then definitely emissive power is equals to absorptive power of that body. One thing you remember, absorptive power definition is quite different. Absorptive power is equals to amount of energy absorbed to the amount of energy, total energy incident. This definition is quite different. Here, this is emissivity definition is different. Emissive power of a given body to the emissive power of perfect. Definitions are different. Their definitions making are different, but they are numerically they are equal. Okay, situationally the number. Numerically, they are number wise they are equal, but their definition wise they are different. Numerically, they are equal. Numerically, they are equal. Right? Okay, their way of defining is quite different. Just number wise they are equal. This is also there. Okay, here this is a dimensional unitless quantity. This is emissivity. This is same ratio of same physical quantity. Okay. Now I will move to the another Stefan's law. Stefan's law. That Stefan's law is also called, even you can call it is Stefan's Boltzmann law also. Stefan's law it is also called another name also, Stefan's Boltzmann law. Okay, two, right? Okay. Because the experimental work is done by Stefan and then theoretical proof is given by Boltzmann. Okay, let me go for it. Here, any object at temperature it radiates. Radiations will come out, electromagnetic waves will come out. Right or not? This energy radiated out in the form of radiation per second is directly proportional to what? Energy radiated per second. Definitely it is directly proportional to area. More the area, more energy will go out in 1 second. And this radiated energy per second, even if directly proportional to, experimentally it has been observed, 4th power of temperature. If you increase the temperature twice, it has been observed energy radiated becomes 16 times. A trial and error, Stefan has experimentally done it. How the radiated energy per second depends on T to the power 4. If you increase the temperature twice, double you make it, the energy emitted becomes 16 times more. So this is a trial and error. He has framed here observed rate of energy emitted out directly depends on 4th power of the temperature. And even rate of energy emitted out is even directly depends on emissivity. You know already what is emissivity? Not only emissive power of a given body to the emissive power of black body. Anyhow, emissive power of black body at temperature is constant. So more the emissivity, more the emissive power. More the emissivity, more the emissive power. So ultimately, so more the rate of energy emitted out, E is more, then E will be more, then ultimately more radiation is going out. This is the, if you combine all, and what you get, rate of energy emitted out is directly proportional to area and is directly proportional to emissivity, it is directly proportional to 4 of absolute temperature. So if you remove this proportional design, there comes one sigma, one constant A E T to the power 4. What is this sigma is called what? Stefan's constant, Stefan's constant, and its value will be 5.67 into 10 to the power minus 8. What should be unit of this? What should be unit? Here it is watt per meter square. This word watt per meter square, K to the power minus 4. As this is watt, area comes down per meter square, T to the, here E is the dimensionless, here K to the power. This is the unit, right? Stefan's constant. This is the energy going out. One thing you remember, because of surrounding, around its surrounding is there, even energy is even hitting or it is incidenting also. Because of surrounding, it is surrounded by some material, even it is absorbing also, right or not? So even it is absorbs also. That's the reason I'll write for absorption at the same. These are all simultaneous process. It is emitting also, it is absorbing also. So if you take the absorption, energy absorbed per second directly proportional to area. More the area, more it will fall on it, and it is even directly proportional to absorptive power here. If it's absorbed, it depends on nature of material. Its absorptive power is more, it can absorb more, and even it directly proportional to temperature of 4 power of temperature of surrounding. If surrounding temperature is more, it can give away more radiations towards it. More radiations towards it. So this is for absorption of this body. When you combine it, absorptive rate of absorption of the energy is equals to, again I will come here sigma proportional distance. What is the rest thing here? A, here this is A, and here temperature of surrounding to the power 4. Now itself I told you numerically absorptive power is equals to emissive power. Now itself I told you. So ultimately rate of energy absorbed is equals to sigma area absorptive power can be written as emissive power and Ts to the power 4. This is the amount of energy absorbed per second. This is the equation, amount of energy radiated per second. Then this is absorbed energy, it is emitted energy. If suppose emitted energy is more than the absorbed energy, then ultimately if it is emitting 10 joule, if it is absorbing 5 joule, then still what you can say? What you can say 5 joule is, it has absorbed 5, it has emitted some amount of energy, say 10 joule if it absorbed, and then if suppose it emitted on 10 joule. Okay, this is energy going out. Suppose energy going out, you can say 10 joule. Energy coming in, you can say 5 joule. So energy coming in 5 joule, energy going out 10 joule. So 10 minus 5 is 5, still 5 joule is going away. So net loss of energy of the body can be written as net loss of energy. Net loss of energy can be written as, let me write here, net rate of loss. Net rate of loss of energy, let me call dq by dt it is. This is net rate of loss of energy is equals to amount of energy gone out minus something is coming in, amount of energy absorbed, going and then absorbing, that gives actual loss. So this amount of energy loss per second is equals to, what is this in place of? The amount radiated will be what here? This is the radiated. Right, I'll write here sigma A e into T to the power 4 minus Amount of energy absorbed is what here? Sigma A e to the power t ts to the power 4. Then what is the equation here? Actual loss of energy of the body is equals to. So what is common here? Sigma A E and t to the power 4 minus ts to the power 4. This is the actual equation of Stefan-Boltzmann law. Here this gives here actual loss in the energy. This is energy absorbed, rate of energy absorbed, this is rate of energy emitted, then actual loss will be this. Sigma is a Boltzmann's constant, Stefan-Boltzmann constant, area of the surface area of the body, and then this is emissivity of the body. Wien's displacement law. Wien's displacement law. Please, anybody, if it is bit fast, again you rewind and see the videos. Okay, this is full of theory and here some equations. Okay, now let me go to the Wien's displacement law. Okay, Wien's displacement law. As I already told you an example, suppose a iron rod, as we increase the temperature, at a particular temperature, at a very high temperature, the iron rod first looks red. First it looks red. Okay, first appearance what you will find iron rod is red. Now further, if you give heat to that iron rod, it slowly appears yellow. It appears yellow, right? Slowly it appears yellow. Okay. Further, if you give, it will turn bluish. You might have observed, right? Bluish. Then what is the meaning of this? As we increase the temperature, okay, when it looks red means what do you understand? Suppose the iron rod is red, looking red. What you what you understand from this? So iron rod looks red because the maximum amount of radiated energy associated with red waves. The bigger quantity of energy is taken away by whom? Red waves. The more energy coming out of this red hot iron is associated with red waves. That's the reason it looks like red. As you keep giving the heat, it looks yellow. What do you mean by this yellow? Yellow it appears because, so it looks yellow because to your eye, the bigger amount of energy carried out by yellow waves. Yellow waves. Our eye can sense yellow means a certain wavelength of range is yellow. Bigger amount of energy taken away by yellow. As you keep giving heat, then it appears blue. It means bigger amount of energy associated with blue. Likewise, as you increase the temperature, bigger amount of energy associated with lower wavelengths. Here red is higher wavelength. As you go here, wavelength lambda decreases. Wavelength lambda decreases. Wavelength lambda decreases, right? Then from this we can, as we take the rod to the higher temperature, the bigger amount of energy associated with lower wavelengths. Then from this, let me frame the equation here. What is the Wien's displacement now? Here, lambda m, what is the lambda m here? The wavelength to which bigger amount of energy is associated. Red, it appears red. The more energy is associated with red wavelength. Lambda is the maximum energy associated, maximum emitted energy associated wavelength is always inversely proportional to the temperature. As I told you, as you increase the temperature, the maximum energy radiated out shift towards lower wavelengths. More the temperature, the energy associated shift towards lower wavelength. So this is what Wien's displacement law. So this can further be written as T is equals to constant, and this constant we say this is one constant V, and this is called Wien's constant. Wien's constant, right? This Wien's constant, okay, this value is 2.9 into 10 to the power minus 3, and definitely what should be the unit of this? This is meter and this is Kelvin. The unit of this will be meter and Kelvin. Okay. Now this is Wien's displacement. Last point I would like to go with energy distribution in the spectrum of black body. Okay, this is, hope you have got this Wien's displacement law. What is Wien's displacement law? So the wavelength corresponding to which maximum energy emitted, the wavelength corresponding to which maximum energy emitted by the black body, we are doing it for ideal things, black body, maximum energy corresponding to particular wavelength, okay, is inversely proportional to absolute temperature. More the temperature, the maximum energy radiate out shifts towards lower wavelengths. This is Wien's displacement law, right? Okay. Now last here, distribution of energy, distribution of energy in the spectrum of black body. The spectrum of black body. Okay. Let me go with a graph here. This is energy associated with different wavelength. I'll take here wavelength in this direction. As that example I given, first it iron rod, first it appears red, and then as you keep giving it, as you keep increasing the temperature, it appears yellow, then it is blue, then the energy associated with wavelength, the wavelength will shift towards lower value. That is here, if you see the graph here, graph will be like that. Like that, you will have graph. Suppose it is at temperature T1, is at temperature T2, temperature T3. Here T3 is greater than T2, is greater than T1. As you increase, okay. Now here, these are all wavelengths. At T1 temperature, suppose this is one black body. It is at temperature T1. So remember, it has got infinite number of emission of 0 to infinity. All wavelength it can emit at any temperature. You can see this is one wavelength, this is another wavelength, different wavelength taking away different energy. This wavelength at the T1, if it is at T1, this wavelength take away this much energy. As the wavelength go, as the electromagnetic wave goes away from the black body, what they actually do, they're taking away energy with them. Electromagnetic waves are form of energy. Well, likewise here, very clearly, here let me take here the maximum energy associated with maximum energy. Okay, maximum energy. If suppose black body at the temperature T1, maximum energy is with this. Let me say this wavelength will taking away maximum energy. Okay, this wavelength. Of course, many wavelengths are there, not as this only single wavelength. Infinite different wavelengths are departing from the black body. So bigger wavelength, smaller wavelength, all possible wavelengths are going away from black body. At this particular wavelength, this wavelength takes away more energy with it. Right? Like red hot, it appears red means what? Plenty of energy is associated with red. As we increase the temperature to T2, the maximum energy shifts to another. So this is lower wavelength, Again, as you keep increasing the energy, okay, somewhere here 3. You can understand. So initially at the lower temperature, the bigger amount of energy corresponding to this wavelength. If you increase the temperature, big amount of energy taken away by lower wavelength shifts here, and keep increasing temperature, bigger amount of energy again shifts to lower. As temperature increases, the wavelength which corresponding to maximum energy will shift lower value, right? This is graph reveals as higher the temperature, the wavelength corresponding to maximum energy radiation shifts lower, right? That is there. And this graph gives, spectrum. What is the area under this? What is this area gives? Area under the graph gives? Area under the graph gives the total energy emitted by a black body per unit area per second. What is this area indicates? Energy emitted out by black body per unit area per second. More the temperature, then the area under this will be bigger, then energy going out from the black body per unit area per second will be still more. As temperature increases, the emissive power will go on increases, the amount of energy radiated per unit area per second increases, right? This is what graph, this is Wien's displacement law, because here wavelength shifts towards lower value as we the energy corresponding, the maximum energy corresponding to the wavelength shifts lower as you increase the temperature, right? So the area under the curve gives what? And total energy emitted or radiated out per unit area per second. The area under curve gives, right? So here with this again even displacement, Wien's displacement will also maximum energy shift towards lower level. As temperature increases, the more energy taken away by wavelength. Which wavelength? Smaller wavelength. This is right. Okay. This video, at first glance, if you are unable to understand it, again repeatedly you see it. It's a bit of full of theory. Again and again you see this, and this will be Wien's displacement law. Now, any doubts you can ask for 1 2 3 minutes. Okay, thank you.